In this video, we're going to show you the Wind Turbine Dynamics experiment, the AE1005V, within the alternative energy range from TecQuipment. Using this experiment, students can learn how wind power is converted to electrical power and understand the relationship between turbine speed and wind velocity for a horizontal axis wind turbine, along with the impact of variables such as blade design, blade pitch and yaw angle. The potential for wind generated power in a given region is determined by the wind power density, which is measured at incremental heights, increasing the higher you go because there are naturally less obstructions further away from the ground as you move further out of the boundary layer of the Earth's surface. Local fluctuating physical, geographical and climatic conditions that affect the wind speed and direction mean that a horizontal axis wind turbine must have the mechanisms to react to those changes. Different turbine designs each have their own pros and cons which you can investigate with this experiment. Let's take a look around it now. The air enters the wind tunnel through the bell mouth at the end here. The air settles as it passes through a honeycomb and the speed is measured by an anemometer, which can be stowed away so it doesn't disturb the velocity field. It features a 400mm diameter wind tunnel which is uninterrupted through the entire length to maximise even predictable flow. A group of students can observe the experiment from both sides through these transparent windows that has a sliding door and interlock. At the base of the unit down here is the yawing mechanism that allows you to turn the nacelle by plus and minus 50 degrees. The anemometer handle is at the front. By using this, students can take an average wind speed across the face of the turbine. The Wind Turbine Dynamics experiment comes supplied with 2 sets of 3 blades, plus the hub CAD file that students can use to base their own custom designed blades for 3D printing. These fit here and are removed with 1 screw. A set of blades can be changed in less than 1 minute. A silencer has been incorporated to the rear. This is detachable and can be stowed underneath to make the unit more compact for storage when not in use. Focusing now on the control panel, which features 2 screens. This allows you to operate the experiment as a standalone apparatus, so a PC is not required. However, for easy data acquisition, VDAS is on board and has been built in. This can be connected to a computer via a USB cable on the side. We'll come on to talk about the integrated VDAS, i.e. VDAS on board shortly. Now here are the controls. There's the on and the off button, the dial for setting the turbine speed, which goes up to 4,000 RPM and can generate up to 70 watts of turbine power. There's another dial for setting the turbine pitch at a range of -5 to 40 degrees, and the last dial for adapting the wind speed. And this is the button to release the interlocking door, which brings me nicely on to talk about the various safety features that have been incorporated. The risk of turbine overspeed or overcurrent has been mitigated by a smart shutdown system. This means if students were to run their 3D printed blades beyond the operating range, the turbine would cut out and shut the airflow off. This same system can detect blade offs due to poor 3D printing and shut the turbine down. The smart shutdown system will shut everything off at an unsafe point to avoid damage. For added safety, there's a protective mesh between the turbine and fan and impact-resistant screens. Earlier I mentioned VDAS on board. This means you don't need to purchase a separate data acquisition hardware unit as it is incorporated into the control panel. By connecting this via USB to a computer with the free software downloaded, you can collect, record and analyse the experiment data. You can chart things such as the effects of blade pitch on power at various speeds and power coefficient against tip speed ratio. These results can be used to prove your custom 3D printed turbine blades against the design theory. As with all products using VDAS, there is the option to utilise the remote lab engagement functionality VDAS eLab. Watch this video for further details on this. For more information about the Wind Turbine Dynamics experiment and other experiments like the focusing solar energy collector, the flat plate solar thermal energy collector, and the photovoltaic cells experiment, click on the links below. We hope you enjoyed this video. Thanks for watching.